Week 9 contents. In this week, we will study work and energy. Here you can see next topic will be impulse and momentum. We will study this topic in week 10 and week 11. In planar kinetics of rigid body, most problems may be solved using kinetic equation of motion plus planar kinematics of rigid body. However, this is not the only option. Work and energy method may be adopted to easily solve many problems involving force, velocity, and displacement. Impulse and momentum method may be adopted to easily solve many problems involving force, velocity, and time. To some extent, these two methods can be treated as shortcuts for solving some problems. The topic of work and energy is relatively easy because work and energy are scalars but not vectors. This means they only have a magnitude but don't have a direction. There are two parts in this week. In the first part, we study how to calculate kinetic energy of a rigid body, how to calculate work done by a force or a couple moment on a rigid body. And then we will study principle of work and energy. In particle dynamics, we know when a particle gets a velocity, it has a kinetic energy. Similarly, if a rigid body gets a velocity, it has a kinetic energy. In previous study, we know general plane motion is the combination of translation and rotation. The kinetic energy of a rigid body in general plane motion is equal to the sum of its translational kinetic energy and rotational kinetic energy. For the calculation, we need select a point in the rigid body in this diagram, for the rigid body undergoing general plane motion, if we select an arbitrary point P to do the calculation, we can work out an equation like this for its kinetic energy. And here T means kinetic energy. You may refer to your textbook if you are interested in how this equation can be worked out. This expression looks complicated, but we can simplify it. We, of course, don't like the complicated expression in our calculation. Actually, we can always use simplified equations. But how to make the equation simplified? Okay, look at this diagram. If point P we select coincides with the mass center point G, this means if we select the mass center point G for the calculation, then in this diagram you can see both x and y in this equation becomes 0. So a simplified equation here can be obtained. In this equation, we can see two components. The first one is translational component. It is related to the velocity of point G. The second one is rotational component, and it is related to the angular velocity. It is easy to find kinetic energy is always positive from this equation. Now, we apply this equation to translation motion, rotation about a fixed axis, and the general plane motion. We will see the equation can be further simplified. Firstly, translation. This rigid body is undergoing translation. This means the angular velocity of this rigid body is 0. So when we calculate its kinetic energy, we only have this translation component. Next, rotation about a fixed axis. And here, this is the rigid body undergoing rotation about a fixed axis through point O. O is the rotation center. G is the mass center point. Of course, we can adopt this already simplified equation for our calculation. And here, we select point G. But because this is the rotation about a fixed axis, so the velocity at mass center point G, Vg, should be equal to the distance from G to O, Rg, times the angular velocity omega of this rigid body. So if we substitute this Vg is equal to Rg times omega into this equation, then rearrange it and use parallel axis theorem, we will get an equation like this. And here, this part is actually equal to IO. So finally, we get this expression. In this one here, we actually select the rotation center point O for the calculation. If point O, the rotation center, coincides with the mass center point G, that means if the mass center point G is the rotation center, then you know Vg, the velocity of the mass center point G, must be 0. Then the equation will be like this. And in this one here, we still select point G for the calculation, but this time we only have a rotational component. Lastly, general plane motion. This is a rigid body undergoing general plane motion. So we can select point G for our calculation. Okay, now if we can determine the location of IC point, and then we have a relationship between Vg and omega and the distance from point G to the IC point. Substitute this into this equation, rearrange it, and using parallel axis theorem, finally we can get equation like this. And here, actually, we select the IC point for the calculation. And you will see this equation is as similar as the equation we worked out for rotation about a fixed axis in last slide. Okay, we can select different points to calculate kinetic energy of a rigid body. But please note, finally, there is only one value. Okay, now, how to calculate the work done by a force on a rigid body? It may be a constant force or a variable force. The force must be resolved to be in the direction of displacement, or more generally, it must be resolved to the direction tangent to the moving path of the rigid body. In this diagram, there is the external force Fc on this rigid body. This Fc is the constant force. This rigid body undergoes a translation from its initial position to the final position, and the displacement is S. Okay, to calculate the work done by Fc, firstly, we must resolve Fc to the direction of this displacement. So that will be Fc cosine theta. Then using Fc cosine theta times S. If F is a variable force, then it will be an integral of F with respect to R. R is displacement. Weight force of a rigid body is constant. is always vertical. Its work is equal to the weight force times the vertical displacement of the rigid body's mass center point G. Is delta Y. So for example here, this delta Y is equal to Y2 minus Y1. 1 means the initial position, 2 means the final position. If we define upward is positive, then in this equation, the work done by a weight force UW is equal to W delta Y. Here, before this multiplication, we always have a negative sign. Here in the diagram, a spring connects to a rigid body. The spring force on the body is not a constant. It is the function of S. Be careful. Here, S is not the absolute length of the spring after it is stretched or compressed. S is the difference between the length of a stretched or compressed spring and the unstretched length of the spring. The integral of a spring force with respect to the displacement gives an equation like this. In this equation, K is stiffness of spring. 1 means initial position and 2 means final position. Not all forces can do work. A force cannot do work if the displacement at the point of application of this force is 0. Here are a few examples. Reaction force at fixed supports cannot do work. Why? Because the fixed support don't have any displacement. That means the displacement at the reactions point of application is 0. Normal force acting on a body cannot do work because the displacement at the point of application is 0. Look at this diagram. And here there is a body is rolling forward. At this contact point, there is a normal force N, and this N cannot do work because the displacement here is horizontal, but this N is vertical. Along vertical direction, no any displacement. Now, friction force. Here, we know for a rolling motion, there is a friction force. If this is a roll without slipping, that means the friction force will be static friction force. Static friction force cannot do work because there is no instantaneous displacement of the point in contact with the ground. And this point should be the IC point. But how about kinetic friction force? If this is a roll with slipping motion, this point, contact point, is not a IC point. The friction force, the kinetic friction force can do work. But what will be the result? The result is heat. Internal forces between bodies cannot do work. Why? Because internal forces always are a pair. A pair of internal forces have same magnitude but opposite direction, so the sum of their work is zero. Next, the work done by a couple moment. When a rigid body subjected to a couple moment M undergoes general plane motion, the two couple forces can do work only when the body undergoes a rotation. Here is the differential equation to show the work done by a couple force. It is equal to the couple moment M times the angular displacement d theta. If the couple moment M is a variable, the work done by this couple moment is an integral of M with respect to theta. If this couple moment M is a constant, the calculation will be much easier. And you can see these two equations look similar as the equations for calculating the work done by a force. If we can always use SI units, for force is Newton, for displacement meter, for velocity meter per second, for angle radians, for angular velocity radians per second, then the unit of work and energy will be joule. Okay, now example. We will use this example to show how to calculate the work done by a force and a couple moment. Firstly, we define this problem. In this problem, you can see there is a bar, and this bar can undergo rotation about a fixed axis through point A. Acting on this bar, there is a couple moment. This couple moment is 50 Newton meter. At the end of this bar, there is an external force. P is 80 Newton. This bar connects to a spring at this point. From this point to point A, it's 2 meters. To the end point, it's 1 meter. Another end of this spring is in a track. This point B is movable. So when this bar is rotating, the position of this spring can be changed. So this bar, so this spring will always keep a vertical position. The task here is to determine the total work done by all external forces, including couple moment, when this bar has a rotation from the position when theta is 0, this means a horizontal position, to a position when theta is 90 degrees, that's a vertical position. And you can see, when we talk about work done by external forces, we always talk about a process. And in this process, at least there are two positions. One is the initial position, and another one is the final position. Okay, now I will solve this problem. For a problem solved by work and energy method, we need a free body diagram to show all external forces. And we also need a diagram to show the process and the positions. So for example, in this problem, we have an initial position. This position, we can define its position 1 when this bar is horizontal. We can define another position. This position is position 2. At this position, the bar is vertical. Okay. We also need a coordinate system. And here, basically, we only need to indicate the positive direction of x and the positive direction of y. And these two positions will be useful in our calculation. In this free body diagram, At the fixed axis point A, we have reaction force Ax, Ay. And here we have a couple moment M. At the mass center point G, this is the middle point of this bar. At this point, we have a weight force W, it's downward. At this point, we can define this point is point C. And here, this point is point C. At this point, we have a spring force. Because the spring can keep a vertical position, so this spring force Fs is always vertical and upward. At the end of this bar, there is external force P. This external force P is direction, is always perpendicular to this bar. So this means the direction of P is always changing. Okay, in this diagram, we indicate position 1 and position 2. So in position 1, G, the mass center point here. In position 2, it becomes G prime. I use G prime, C prime, and D prime to show the point in position 2. Okay, we already know the mass, external force P, couple moment M, the stiffness of this spring K, the unstretched length of this spring 0.5. The target is the work done by all these external forces. So this includes US, work done by the spring force, UW, the work done by weight force, UP, the work done by the external force P, and UM, the work done by the couple moment. Now, solution. So the first one is the work done by the spring force, US. And that's the only available equation for this calculation. And here, using this equation, we normally put S2 before S1. So before this difference, we always have a negative sign. Okay, here K is already known. It's the stiffness of the spring. We must work out S2 and S1. S1 is the difference between the absolute length of the spring and the unstretched length of the spring. The absolute length of the spring in position 1 is BC, and this distance can be obtained in the diagram. It's 0.75. The unstretched length of this spring is 0.5, so S1 is 0.25 meter. S2 the absolute length of this spring in position 2 is equal to the length of B prime to C prime. From B prime to C prime, this distance is equal to B prime A plus A C prime. So that will be 0.75 plus 2. And then minus SO, the unstretched length of the spring, 0.5. So S2 is 2.25 meter. Okay, substitute S1 and S2 into this equation. We can work out the work done by this spring force is negative 75 joule. Okay, the second one is the work done by the weight force. The equation is negative W times delta Y. Delta Y is equal to Y2 minus Y1. Okay, Y2 is equal to the distance from A to G prime. This should be half of the length of the bar, so it's 1.5 meter. So this means for delta y is the vertical distance from G to G prime. This should be 1.5 meter, and it's negative 1.5 meter. So the work done by the weight force is 147.2. For P, external force. In this diagram, you can see, because this P is always perpendicular to this bar. So this means if we look at the moving path of this end point D, this moving path should be a part of a circle, and this P, its direction, is always tangent to its moving path. And that means the angle between this external force P and the displacement of this acting point of application is always 0. So here we use this equation because P is the constant force, so we can use this equation. And here the angle theta is 0. S is the distance. S is the displacement, and this displacement is equal to the length of the arc D prime. This is the quarter of a circle, so we can easily calculate this D d prime. And then finally, the work done by this external force P is 377.0 joule. Last one is the couple moment. This couple moment is a constant, so we can use this equation. In this equation here, delta theta is the angular displacement from this horizontal position to this vertical position is angular displacement. Delta theta is half pi radians. So finally, this will give us 78.5 joule. Okay, now the total work done by all these external forces add up. They are all scalars, so just simply add up. We can get 528 joule. Okay, next, we introduce principle of work and energy. In particle dynamics, we already learned principle of work and energy. And here, for a rigid body, the meaning of this principle of work and energy is as similar as the meaning of the principle of work and energy for a particle. And that's the expression. We know work and energy can convert into each other. So this principle, work and energy, is actually an expression of energy conservation. This equation tells us in a process from an initial position to final position, the initial kinetic energy T1 plus the work done by all external forces must be equal to this rigid body's final kinetic energy T2. How to calculate T1, T2, and work done by external forces, we have already known in our study in previous slides. Okay, next, we use this example to show how to use principle of work and energy to solve a problem. So firstly, let's define this problem. And here, there is a wheel, and this wheel is subjected to an external force P. So this force P will drive this wheel rolling forward, and this is the rolls without slipping motion. Here, rolls without slipping. This wheel starts from rest. So that means its initial velocity is 0. The task here is to determine the angular velocity of this wheel after it has rotated 10 revolutions. Okay, so you can see this problem involves external force, velocity, angular velocity, and displacement, angular displacement. It has rotated 10 revolutions. Solution. After defining this problem, we already know this wheel undergoes general plane motion. This is the rolls without slipping. It's general plane motion. Because it rolls without slipping, so the friction between the roll and the ground must be static friction force. Static friction force does not do work. Okay, a diagram. This is the free body diagram, and we define this coordinate system. And here, external force P, weight force W acting at this circle center, also the mass center point O. At the contact point between this wheel and the ground, we have reaction force N and the static friction force F. Using the method we introduced before, we can get the direction of this friction force. Step 1. We assume no friction at this contact point. If no friction, what will happen? Driven by this external force P, this wheel will be undergoing translation to right side like a block. So at this point, the direction of this friction force must be opposite. So it should be to left side. Okay, for this one, I didn't give a diagram to show the initial position and final position. But it is very clear this wheel will be moving from this initial position to a final position at here. Okay, external force P, 50 Newton, M, the mass of this wheel, 50 kilo, radius of gyration of this wheel is 0.3, so we can easily calculate its MMI about an axis 0.0. Omega 1, initial velocity, angular velocity, 0. Delta theta is the angular displacement. It's 10 revolution. Revolution is not a SI unit, so this should be converted into radians. Okay. The equation is this one for principle of work and energy. Firstly, we calculate MMI of this wheel about an axis 0.0. So this will be MKO squared. Now we calculate T1. This wheel is undergoing general plane motion, so we can have two components. This one, translational component related to the velocity at point O, V01. The second component, rotational component, this one is related to the initial angular velocity omega-1, because initially the velocity must be 0, so T1 must be 0. T2, still two components. VO2, omega-2, we don't know. There are two unknowns. But VO2 and omega-2, they are not independent, because this wheel rolls without sleeping, and the contact point between the wheel and the ground A is IC point. So we can easily get the relationship between VO and omega. VO2 will be equal to omega-2 times the distance from O to A, so VO2 is equal to 0.4 omega. Substitute this into this equation, so finally we have only one unknown here. It's omega-2, and this is T2. Okay, now we have worked out the initial kinetic energy and the final kinetic energy of this wheel. Next, we will calculate the work done by external force. And here, the external force, the only one that can do work is this external force P. Look at this diagram. For this weight force W along this vertical direction, no any displacement. So the work done by this weight force should be 0. For N along this vertical direction, no displacement, so the work done by this reaction force N is 0. The work done by this friction force F should be 0, as mentioned before, because this F is a static friction force. P is a constant, so we use this equation. And S is the displacement of the acting point of external force P. And this is equal to the displacement of the circle center O. The angle between this external force P and the displacement, the displacement is a translation displacement. This angle is 30 degrees. Okay, now this S. We already know this wheel, its angular displacement delta theta is 10 revolutions. One revolution can give us a distance of the circle center 2 pi r. So finally, we can work out. The work done by this external force P is 1088 Newton meter. Okay, substitute T1, T2, and the total work done by external force into the equation. Only one unknown parameter, omega 2, so this can be worked out. It's 13.2 radians per second. And its direction, omega is the vector, so it has a magnitude and it has a direction. This direction can only be determined by observation. In this one here, it should be clockwise. Okay, so that's the solution of this problem. Principle of work and energy may be adopted as a part of the solution in some problems. For example, this problem. In this problem here, there is a pipe suspended from the two tines of the forklift. This pipe is undergoing a swinging motion. And we already know one its angle theta is 30 degrees. It's momentarily at rest. The task here is to determine the normal and the friction force acting on the tines. This normal and friction force should be able to support the pipe when this theta is 0 degree. That means when this pipe is at its lowest position. So two positions. Position 1, initial position, is when this theta is 30 degree. The final position is the position when this theta is 0 degree. Okay, how to solve this problem? If we define this problem, we will see the target of this problem is to work out when this pipe is at its lowest position, the reaction force at these two times. NO. If we define this point is O, that's NO, reaction force NO, and friction force FO. This problem looks as similar as the problem we solved before when we studied kinetic equation of motion. We can focus on this instant The target is NO and FO, and this pipe actually undergoes a rotation about this point O. This NO and FO can hold it. You may remember when we solved a similar problem before using kinetic equation of motion for this kind of problem, we normally has an instant, and at that instant, this rigid body, for example, this pipe, is at rest. Or we might be given the velocity of this rigid body at this instant. But here, the difference is we only know when theta is 30 degrees, this pipe is at rest. We don't know the velocity when this pipe is at its lowest position. So how to solve this problem? Before we can solve it, we must know the velocity of this pipe when it's at its lowest position. So firstly, we have to use a method to work out this velocity, and this problem is a problem involving force. The force is weight force, velocity, and displacement. Displacement is from here to here, so the angular displacement delta theta is 30 degrees. Then after we can work out the velocity when this pipe is at its lowest position, we can use kinetic equations of motion to work out NO, FO, and angular acceleration at this moment. Okay? So in this problem here, work and energy can be adopted as part of the solution for solving omega 2. So here I have this free body diagram when this pipe in its initial position, position 1, and a free body diagram when this pipe is at its final position, position 2. I have this coordinate system x, y, and the first step is to determine omega 2, and we use work and energy method. Okay, we can consider the pipe to be a thin ring, so its MMI about its mass center point G. G should be the circle center, will be mr squared. And this equation can be found from the equation page for MMI of several rigid bodies. Because the rotation center of this pipe is 0.0, so we use parallel axis theorem to calculate MMI about axis 0.0. Then we adopt the principle of work and energy. Initial kinetic energy T1 is this. This is the rotation, so we also can use this equation. They are actually same. In initial position 1, because velocity is 0, so actually T1 must be 0. Okay, now T2. For T2, we can use this equation. Select point G for the calculation. So we have two components, Vg2 and omega-2. They are not independent, and Vg2 can be expressed using omega-2 times the distance from G to O. Okay, substitute this into this equation. We only have omega-2. So the final kinetic energy, T2, is equal to 63.88 omega-2 squared. To calculate T2, we can also select this IC point. This IC point is the point O. We can get the same result. Work done by external force. In this problem here, the only external force that can do work is this weight force W. The displacement for this weight force W is from here to here. This vertical distance can be worked out using this calculation. This is trigonometry. Okay, now we use this equation for the calculation. So we can get the work done by the external force, the weight force is 368 joule. And finally, using principle of work and energy, we know omega-2 is 2.4 radians per second. Okay, now, if we can work out this omega-2, then we can go to next step using kinetic equations of motion to work out reaction force NO and FO. And this time, we use a normal tangential coordinate system. Define this vertical direction is N. Upward is positive. Define this horizontal position is T direction, and the positive direction to right side. And now we need a free body diagram and a kinetic diagram. In this free body diagram, we indicate weight force at this instant, this pipe is in its lowest position. Here at point O, we have NO and FO. In this kinetic diagram, we give alpha, we give AGT and AGN. Okay, we already know the mass of this pipe. We already worked out angular velocity at this instant is 2.4. Using kinetic equation of motion and based on this defined normal tangential coordinate system, so we can establish three equations. One is along tangential direction. Along tangential direction, we only have one external force, Fo. And this must be equal to M700 times AGT. AGT and alpha, these two are not independent. Because at this moment O is the rotation center, so AGT can be expressed using alpha. If alpha here in this diagram is direction, we assume it's positive counterclockwise, then AGT, this direction, must be to right side, positive. Along normal direction, we have two external forces. One is NO, this one upward positive, and W, this one negative. Okay. On the right side, that's MAGN, M700. But how about AGN? AGN can be worked out using omega square times R. R is the distance from G to the rotation center at this moment O. Omega we have already worked out. So finally, NO is 8.48 kilonewton. The third equation is about the rotational component in this kinetic equation of motion, and this calculation can be about point O, the rotation center at this moment. Okay, at this moment, if we look at this free body diagram, we can see about point O, the moment of all external forces are zero because their moments are zero. On the right side is equal to IO alpha. Okay, now from this equation 3, you can see alpha must be 0. Then substitute this alpha into equation 1. We will find FO, the friction force at point O, must be 0. Okay, now because there are 2 times, so for each time, the normal force N on each time should be half. That will be 4.24 kilonewton. So that's the solution of this problem.